learning the 3D structure of objects. And the third thing is to learn from data in the wild, which I would say is very...
By the way, I think, do you want to share your screen? It's not sharing yet.
Oh, it's not sharing. Okay.
Yes.
I was looking at slides before, but okay. There you go. Can you see that?
Yes, perfect.
Okay, great. And maybe let me just put this in play mode so we can present mode. I think it's this button here. Yeah, okay, great. Yeah, so anyway, without further ado, so we have a great day in front of us. It's a very long day with which is packed with very, very good speakers. You can see here in one slide all the people that are going to speak today. These are the organizers of the workshop. Yeah, so again, this is a workshop about learning from unsupervised data that doesn't have labels, or which could mean no manual labels, but could also be no labels in terms of 3D information, like, for example, recording done with point clouds obtained from a LiDAR, but rather just raw images and videos. And the goal here would be to take this sort of data which is available, for example, on the internet in abundance, and extract from that a three-dimensional understanding of the world. Now, this gives you some very exciting experiment, colorful results. You can see here a composition slide where we show some of the cool stuff you're going to probably see today, results from recent papers from the speakers. And it looks very nice. It's a fun data to work with, but it's also, in a certain sense, fundamental and important. So that's, I believe, or we believe, one of the important next step in computer vision to be able to finally break through these kind of problems. All right, so in terms of a program, these are times in Eastern time, so presumably where ICCV is supposed to be located, except that it, of course, is running virtually. And so we're going to have 3 blocks of talks, of 3 talks each. Sorry, 4 blocks of talks of 3 talks each. After each block, we're going to have either a short break or a longer break. We're also going to have panels at the end of at the end of pairs of blocks. During the long break, basically lunch break, there will be an opportunity to talk to each other using a platform that we're going to discuss in the next slide. So here you can see on a glance the people that are going to speak in which order. But if you want to have more information about the details of the workshop, the talks, the times, and instructions on how to ask questions, you can connect to this URL on GitHub. This is ASAP 3D. Again, so you're going to get information about today's schedule, as well as instruction on how to watch this. Of course, there is a Zoom channel to which you're probably connected. There should also be a YouTube live stream, which where we're able to start that.
Yes, it's live streaming.
Exactly, great. So the workshop will be recorded, so keep that in mind, please. So if you want to type questions for the speaker, you should be using the Zoom channel. All right, that's the primary way you can do that. Of course, you can use that only if you are registered to ICCV. So it is possible to enter questions in the YouTube live stream as well. We'll try to monitor that too, but we cannot guarantee that we'll be able to go through those questions in full. Again, talks will be recorded, so you'll be able to watch them later, particularly for the ones that are not inconvenient time zone for you. And again, so during the long break, we will be able to talk to each other using this platform, which is called Gatheredly. And maybe, Shanze, do you have some more details about that?
Not yet, unfortunately. The ICCV organizers haven't given us the details on this. We'll try to release it, okay, the details once we have it.
All right, that's great. So a little bit of last-minute excitement. We are going to update the information on the website, and of course, during the breaks, we're going to tell you if we have news on this. All right, now I think that's enough chit-chat. So going back to our list of talks, the first one to be speaking is Tali. So are you? Oh yeah, here you are. So please, the stage is yours.
Okay, I'll give a little bit short introduction for Tali. She's an amazing researcher, and she's currently a assistant professor in the Department of Math and Computer Science in the Weizmann Institute of Science. And he was a research scientist. He's also a research scientist at the moment at Google as well, I think. And she's done amazing work on image and video analysis and multi-view reconstruction, 3D structure from motion, etc. And including the best paper award at the ICCV 2019, the SINGAN, and the Mannequin Challenge, which won the best paper honorable mention award at CVPR 2019. So Tali, please take over and show us the latest work. I think you're muted.
Yes.
Oh. Okay.
Hi everyone. Very excited to be here. And thanks for the introduction. So I know this workshop focuses on kind of learning 3D in the wild, but this is such a challenging topic. So instead, I'm going to talk about 2D methods and more specifically about layered neural representations for videos. So recently, I've been very interested in how can we analyze and re-render casual everyday videos. So this is a sample of my own personal video collections. Most of these videos are of my children, and I take many of these videos and I care about them, but I hardly watch them because even for me, those videos are kind of boring. So I was looking for ways to make these videos much more engaging, artistic, creative, and more generally, looking for ways to enhance the way we can perceive our dynamic world through everyday videos. So just to give a few examples, here is a video where we told the children to jump to the pool together, but of course, each child jumps at a different time, as you can see here. So what I'm going to show you next is a result produced computationally and automatically, in which we go into the video and retime the motions of the children such that they all jump to the pool together. So here is the result. And now notice how not only the children are retimed, but also all the scene elements that are related to them. The water splashes, the reflection in the water, all these complex scene elements are nicely following the children in the retimed result. So going into the video and changing the actions and the moments that actions occur in the video is one way that we can perceive the way we can enhance the way we perceive kind of actions in a video. So here is another example. Oh, got stuck. Sorry. Slides get stuck. Here is another example where we take this ordinary video of a horse jump and we can produce this stroboscopic video where, again, you can see that not only the horse is being duplicated, but also the shadow is nicely casted on the ground. Another useful application is removing objects from video. So here we have a bunch of children jumping, causing deformation to the trampoline. And we can remove all the people except once. And again, we can remove those people along with the deformation effects that they generate in the scene. And finally, this is a final example where we take this video and we want to map objects or map texture onto object in this video. And we want everything to continue to move in a coherent way. And also you can see that the shadow here is casted on the bench, the colored bench, in a realistic manner. So all these video editing effects were produced by different methods from the past couple of years. At the heart of this method, there is a decomposition of the video into layers, but each kind of work focuses on a different aspect of the decomposition. And today I'm going to tell you a bit about Omnimatte from last CVPR, and then I'm going to tell you about the new work, the layered neural atlases that will appear at SIGGRAPH Asia this year. Okay, so let's jump into it. And Omnimatte is a joint work with Erica Liu, Forrester Cole, Mickey Rubinstein, Andrew Zisserman, and Bill Freeman from Google. And let's think for a second what is required in order to produce all these effects that I showed you. Obviously, we need to segment out the objects, but it's not enough. We also must take into account all the scene elements that this object generates in the scene. And actually, computer vision became really good at segmenting objects. So what you can see here is a result of a state-of-the-art, segmenter, Mascar CNN on this complex video. So it works fairly nicely. But if we take those masks and plug them into kind of like a state-of-the-art object removal method, this is the result we get. So we end up with all these kind of like visual artifacts because we didn't model, we didn't take into account the deformation of the trampoline in this example. So video editing and the applications that I just showed you give rise to these novel research questions of how can we associate objects in video with their scene effects. And that led us to define a new problem, the Omnimatte problem. So this is the setup. We have an ordinary video along with rough masks for each object of interest. You can compute those masks using off-the-shelf tools like Mascar CNN. And the goal is to produce an RGBA layer for each object. And those layers not only contain the object, but also all the scene elements that are correlated with them in the video. So for example, shadows, reflections, smoke, etc. We also have one separate layer for the background. And of course, the task of decomposing a video into layers is not new. The pioneering work by Wang and Edelson inspired a great body of follow-up work. And modern approaches, of course, use the power of deep learning. So for example, in stereo magnification, you take a narrow baseline stereo pair, and they basically learn a layered representation that corresponds to physical depth layer. And then they can generate like wider baseline views of the scene from this layered representation. In our case, we are also using the power of deep learning, but our layers are not meant to be strictly accurate in terms of depth. Our layers meant to capture an object along with all the effects that they generate in the scene. And our model is trained on a single video without observing any additional examples in a self-supervised manner. And the main driving loss that drives this whole system is a reconstruction loss. We want the layers, when we put them back together, to allow us to reconstruct the original video frames, as you can see here. So let's dive more into the details. We're given a video, and for each frame of the video, we have these rough object masks that we computed. We also pre-compute optical flow between consecutive frames using, for example, Raft. And we have our Omnimatte model. We take, so a mask and an optical flow form the input for a given layer, and we input those input layers into the Omnimatte model in a separate forward pass, as you can see here. The Omnimatte model produces outputs an RGBA layer and also a refined flow layer. So optical flow layer here is just an auxiliary task that allows us to inject kind of like motion information into the model. For the background, we also have a separate background layer, and we assume that the background is static, and the motion of the background can be well approximated using homographies. So that means we can register all the frames into a common coordinate system. And in practice, we just have a single background layer for the entire video. The input is just a fixed noise image, as you can see here. And the output is the unwrapped background canvas for the full video. So in order to get the background layer for a specific frame, we just need to sample this background layer using the pre-computed homographies. You can see the paper for more details, and even if you didn't get all the technical details here, it's not so important. What is important to get is that we model only a static background and the objects. And this model is required to faithfully reconstruct the entire video. And in order to do a good job, it must also reconstruct all these time-varying scene elements, like this shadow on the ground here. But these elements are not given to the model as input by any manner. So the model is required to infer reflections, shadows, and all these complex scene effects automatically. Okay, And now the key question is, how does this model manage to place the effect in the correct layer, right? How does it manage to associate the effects with the object causing them? So I'm going to give like a very kind of like brief and intuitive explanation to make this point. Okay, so recall that this network is overfitted to this single video. So basically it has to memorize this shadow given the inputs that we provide. Recall also that we assumed that the background is static, so the network cannot place this shadow in the background layer. It must place it in the object layer. So it has the option of predicting this shadow from the person's input, the person's mask and flow, or it can predict it from the dog's input. And it has to do it consistently over the entire video. And if we take a look of this task over the entire video, what we can see is that obviously there is very high correlation between the person's input, the mask and optical flow, and the shadow. We can tell a lot about the shadow by knowing the mask of the persons and the optical flow. On the other hand, the dog doesn't tell us much about the person's shadow. So it's a much more difficult task for the network to predict the person's shadow from the dog's input. So in short, the shadow can be learned quicker and in fewer iterations from the person's input, and that's the solution that the network favors. So this is also, very much related to the observation made in the deep image prior work, if you're familiar with that, where they show that if you take a CNN model that is trained and you fit it from scratch to an image, it's a much easier task for the model to fit a natural image than a random noise. So for natural images, there is high correlation between image patches, and it takes fewer iterations for a CNN to learn to kind of like reconstruct a natural image than random noise. In our case, the effects that are closely correlated with an object in space, in time, or in both are learned quicker and in fewer iterations than other effects that might be noise with respect to that input. Now, this is only kind of like a very intuitive and a brief explanation. We have a more in-depth analysis in our SIGGRAPH Asia 20 paper, so please check it out for more if you want to know more about how it works. So just to conclude kind of like the losses that we use. So as I mentioned, the main driving loss is a reconstruction loss. We want the layers when we put them back together to allow us to reconstruct the original video frame. We also have a regularization on our alpha mets. We want them to be sparse, and this is a combination of an L0 and L1 loss on the alpha mets. And it turns out that these two losses alone are not enough to make the optimization converge from a random initialization. So we also have an initialization loss in which we encourage the mask of each layer to match kind of like the rough segmentation mask that we use as input. We turn off this loss after several epochs and let the network refine this initial estimate. Finally, we have two additional losses that incorporate the flow. One is a temporal consistency loss, and the other is kind of like flow reconstruction loss, which is similar to the RGB losses. Okay, so let's see a few examples. Here you can see results from Davis. You can see on the left the original video, then the input mask that we use as input, our Omnimatte prediction, the RGBA layers for both the foreground and the background. So you can see here how we manage in the Black Swan example to pick up all those complex reflections in the water and also very fine details of the swan. In the second example, we're able to pick up the dust that this elephant throws, and you can see kind of like the delta from the input mask. And here in the last example, you can see how we capture the shadows that does not appear in the input mask, the original input mask. So overall, if you take a very close look, you can start to notice a few artifacts. Like for example, in the Black Swan, you can see a little piece of the swan in the background, because the model never observed the content behind that region, and so it doesn't have a good guess how to paint this. But overall, kind of like the results are you know, we are able to apply this method on a really diverse set of objects and across categories and capture those semi-transparent complex effects. And now that if you have those layers in hand, you can do all sorts of kind of like, you know, video effects. So here, for example, we can do color pop. We can keep in color only the flamingo and its effects, and the rest is left in grayscale. So here is the result. Sorry for the lagging in the videos. This, I guess, Zoom challenging me. So please check out the videos also offline later. This is a real application where we were asked by a team to take this video and place a logo behind the car on the ground. So we used our Omnimatte to separate the video into background and foreground layers, and we were able to separate out the smoke and place the logo right below it. And here you can see kind of like the RGBA layer for that video. And, you know, just imagine to do this in Photoshop. This is really, really challenging. Okay, so I guess Omnimattes are great for associating objects and their effects in video, but one disadvantage of this representation is that it is a per frame representation, meaning we take the video and for each frame I have an RGBA layer. But you know, the editing is kind of like restricted to per frame manipulation. I don't have a good way of propagating information across time here. So in this work, like a new work, which in neural atlases, our goal was to tackle this challenge. Here, the idea is as follows: we want to take exactly the same input like the original video, just a casual video, but now we want to break it not into per frame RGB layers, but instead we want to have per video atlases, 2D atlases layers. And this provides us with a unified representation of the video that will allow us to easily and intuitively edit the video across time, as I'll show. This is a new work, a joint work with Yoni Kasten, Dolevo Free, and Oliver Wang, and it will be presented at SIGGRAPH Asia this year. So again, the idea is that we want to take an input video and break and decompose it and unwrap it into these 2D atlases. So you can think of these 2D atlases as texture map, only that we don't have a 3D model of these objects behind the scenes, right? Like you might have like in dense pose. Here, everything is 2D. And, you know, imagine like what, it would be very challenging to have like a very accurate 3D model of this swinging dress. So instead, what we do here is our method not only estimates these 2D atlases, it also directly estimates a mapping from each video position onto this set of 2D atlases. And what this allows us is to basically apply any editing that we want directly on these 2D atlases, like we can color the bench or add those flowers onto the dress. And then using the mapping, we can consistently map them back into the video, to the original video. So all that was required to produce these results is editing 2 images. That's it, 2 texture maps. And of course, this idea of unwrapping a video into kind of like a unified texture map is actually not new. Our work is inspired by the unwrap mosaic methods from 2008. But, you know, this was before the deep learning area, and it was a very complex and very sensitive system, and that has several kind of like drawbacks that we actually try to tackle in our work. So one problem with the unwrap mosaic is that it assumes an input and accurate segmentation mask for the object. It doesn't refine the mask, it doesn't solve for decomposition, whereas our method solves for a layer decomposition. Like in Omnimatte, we only use the segmentation mask as initialization, and then we refine them together with the rest of the unknowns that we estimate. And another problem with the unwrap mosaic is that it relies on very long point tracking in the video, which is super challenging. In our case, we only use pairwise optical flow and only use it as a soft constraint. Finally, they have kind of like a discrete atlas. They have to set the resolution in advance, And we leverage continuous atlases via coordinate-based MLPs. Okay, so in more details, given a video, each pixel position, x, y, t, is first mapped onto these 2D coordinates in the atlas space. So these are just like values between -1 and 1 that tells us, you know, for each position, where does it map to in the atlas. These estimated 2D points are then fed into another atlas MLP network that predicts the corresponding RGB color at that atlas location. So what you are seeing here is just kind of like a rendering or a visualization of this continuous atlas when we render it into a discrete image. Each atlas position also goes into an alpha MLP that produces an opacity value that tells, you know, at this pixel position, how much is observed from each atlas layer. And this allows us to basically reconstruct the color at video position P just using alpha blending. And this essentially allows us to reconstruct the original video and to train this whole thing end to end, mainly relying on a reconstruction loss as we did in Omnimatte. Now recall that our goal here is, you know, to edit the video. So we want to produce atlases that will be interpretable and that will preserve the video content and that will have several properties. So reconstruction alone is not enough. We have several loss terms in our objective function, and I will briefly explain each one of them, okay? So as I mentioned, the main loss is a reconstruction loss. We just want, you know, this representation to allow us to get back the original video content. So this is just a simple L2 loss between the original colors of the video and the predicted ones. The second term is a rigidity loss. Our goal is, again, to get interpretable atlases. So we want the content in the atlases to preserve as much as possible the original structure in the videos. So we achieve this by encouraging the mapping between a video frame onto the atlas to be locally rigid. And without this loss, you can see that the atlases are kind of like all very much distorted, and they all collapse maybe into a very small region in this kind of like continuous atlas space. So the rigidity loss prevents this. We have an additional loss that is based on optical flow. So ideally, what we wanted to achieve is that, you know, each point in the atlas domain will correspond to a physical point in the world. And again, we don't have any 3D information. So our way to kind of like encourage that is through 2D optical flow. What we want 2 points when the 2 corresponding points to be mapped to the same point in the atlas space. So this loss encouraged that using a pre-computed optical flow. So here you can see the results when without this loss. So surprisingly, I was surprised to see that it's not like the model completely breaks. It still managed to do the decomposition nicely and still managed here to get a nice foreground atlas layer. But you can see, you know, some artifacts and objects that break in the background on the right here. And the optical flow prevents that. The problem is that we don't have optical flow for all the pixels in the video. Some pixels won't have kind of like valid optical flow. And in order to kind of like prevent duplication in the atlas domain and deal with those points where we don't have supervision for, we also have a sparsity loss that encourages a minimal alpha atlas. So without this loss, you can see that we might get kind of like duplication, like we get 2 motorbikes here in this example, and the sparsity loss will encourage kind of like a minimal atlas. Okay, so just to recap, our losses are kind of like, we want to reconstruct the original video. We want to preserve the original structure in the atlas. We want corresponding points to be mapped to the same atlas point. Finally, we also want the atlas to be minimal as possible. And with our full model, we are able to get this decomposition for that video. We also have an alpha initialization stage where we can get kind of like a very rough mask. So, you know, for some object category, mask RCNN might not work like here. So actually we experiment with that, and the model works well also with very rough user mask like you can see here, and it refines them during kind of like the optimization. So let's see some more results. Here is an input video. You know, there is quite a bit kind of like of motion in the background here. And here you can see the foreground and background atlases that our model produces. You can see some distortion in the car, but again, locally, everything remain rigid and allow us to apply all sorts of editing. So here you can see kind of like also the reconstructed video, the RGB foreground layer, which you can see that capture also the shadow and reflections. And you can see also an example where we map a texture onto this car on the top right. Is an even more challenging example that has like, you know, very severe parallax and complex non-rigid motions. And here is the decomposition for the foreground and background atlas. And again, you can see the reconstruction, the RGBA layer, and the texture mapped onto this object. And this is, again, a super challenging example. So as I mentioned, like with respect to the unwrapped mosaic, we are using a continuous representation of the atlases and mapping. And in order to show the advantage of that, we did a small ablation where we just replaced the continuous atlas with a discrete atlas. You have an image, and the pixel of that image is the unknown. And now we just want to solve the same objective function. Everything is the same, just replacing the MLP atlas with this discrete image. And this is the result you get for this dog video. And you can see that the composition really breaks. So actually you can get like, even with kind of like this really bad decomposition, you could get a pretty okay-ish reconstruction, but the decomposition is meaningless and you won't be able to do much with, you know, these atlases, as you can see here. So the fact that we're working in a continuous domain allows the model to be much more flexible. You don't need to set the resolution in advance, and the model could give a different budget to different kind of like region in the atlas as it needs to. Okay, so let's see some cool stuff that we can do with that. So this is a video, again, sorry, this is again my son, and this is the foreground and background atlases. And to do editing, what we do, we just render those atlases into images, and then we can just plug it into any editing tool that we want. So for example, we can just, you know, apply existing image style transfer on this texture image, and then map this stylized background atlas back to the video domain using our mapping and get this result. And again, all we have to do is just kind of like edit a single image, and it automatically propagates continuously in time to the video. We can do this to this black swan example, this time for the foreground object, just by applying some Photoshop filter. And you can see how, because we are solving for the decomposition, we are able to also edit the reflection in the water, not just the swan itself. As I mentioned, we can map texture onto objects. So in this complex video, what I just did, I just kind of like laid out some stars and this pinkish line on this, you know, the white region in the background atlas. And then we're able to basically map those stars. The stars will deform with the wave, and they will settle down once the waves is gone in the video. So regarding limitations of this approach, I mean, because we have these rigidity constraints that we apply to the video, it will be kind of like challenging to represent very complex geometry and self-occlusion and extreme deformation with a single foreground layers. Like in this example, this is a super challenging example, and you can see that our foreground atlas doesn't represent reliably the full body parts. And in this case, we need to break the object layer, the foreground layer, into multiple foreground layers to reliably kind of like represent this. But still, you can see that even in this example, the predicted alpha and the background atlas are quite of good quality. So in fact, we are still able to edit this video by, let's say we can just add this graffiti on the ground and this scribble on the wall, and get this as a result and map them back to the video. So though we didn't manage to fully kind of like represent the persons and we cannot edit the person here, the result is still useful. Okay, so I think with that, I'd like to end. I just want to acknowledge again all the wonderful people I got lucky to work with on all these different projects. And just to conclude, I guess each of those works kind of like reveal the different aspects of layered decompositions of videos. I think this is a really exciting topic that allowed me at least to be much more creative and fun with my own personal videos, and also kind of like, raises a fundamental question of, how to represent temporal content in everyday videos in a meaningful way. So with that, I'd like to end there. I can probably take a few questions. So thank you all.
Yeah, thank you very much. It's those are really, really cool results. I really love all those editing effects. I do have a question here. Of course, participants, feel free to type the questions in the chat, and we'll ask the speakers as well. So how much 3D do you think you can extract from these representations, like atlases, or from the Omnimatte? I guess with the alpha maps, there might be some information about the 3D layout.
Yeah, so I think for Omnimatte, it's less obvious to me that you would be able to easily extract 3D. I think the neural atlases it's 2.5D, right? It's a representation that has this kind of like, unified representation, like each point of the atlas is mapped back to the video. And you can start imagining that, you can track a point throughout the video, and perhaps that could give you a lot of prior about how to extract its 3D information. Or you can start thinking of really integrating kind of like a 3D model in the loop together with these 2D atlases, like making the whole thing a real 3D model. So an example is dense pose, right? Like you can imagine that you could solve for this UV mapping, but maybe you also want to solve for a mesh that will tell you where each point is kind of like located in 3D. I think it will be challenging, but I think it should be possible.
Awesome. Yeah. I think all the results, it might be really possible. Like if you have all these light atlases, it might be possible to visualize them from another viewpoint somehow if you project them onto 3D.
Yeah.
Amazing.
Should I take some question from the chat then?
Yes. So there is a question that is what would happen to the layer decomposition if the camera movement is very large?
So in which work? So I guess in the Omnimatte, we did assume a static background and we also assume that, you can well approximate the camera motion using homography. So I guess in that case, the model will struggle if you cannot do that, because we won't be able to register all the frame into a single coordinate system. In our neural atlases, we don't have this assumption. So we can deal with arbitrary camera motion. And I think we've seen one, like in the Libby example, the camera motion is pretty fast and it has a lot of parallax. So I think, again, to deal with really correctly, parallax, you might want to break things into kind of really depth layers and do this correctly. But for these types of videos, the model was able to handle them quite nicely.
Cool. There's also another question, which is like, could we use this atlas for advanced like video compression?
Yeah, so I think there is this classical work called video epitomes. I don't know if you guys familiar or remember this work. So I think there it's quite similar. They have this mapping onto this kind of like a minimal map. But I guess our focus was to have atlases that are interpretable and that we can edit. I think that for compression, you can drop this assumption. Yeah, and this requirement, and you can think of like maybe you can compress a video in a way that that will collapse everything into a very small region in the continuous space. But I think it's an interesting direction. I think the requirement, the objective requirement, would be different in this case.
Cool. One last question, which is what is the computational cost of these models as it takes to like overfit on one single video?
Yeah, so I guess it changes. So for Omnimatte, it changes, according to the number of layers and the number of frames. Also for our neural rendering, it depends on your GPU power and so on. I think it took a couple of hours, several hours on a single video that had, I don't know, multiple, like standard Davis video, probably on 2P100. We have all these details in the paper. I can't recall the exact numbers right now, but it's not a super fast method yet. Hopefully it will get there at some point.
Awesome. I think that's all the questions. Thank you very much, Tali. Thanks for joining us.
Thank you so much for inviting me. It was great to be here. Thanks.